Good evening, everyone. Today, Group 3 will be presenting you an overview of Chapter 5, which deals with system verification, validation, and testing methods, with special emphasis on testing. Our group consists of team members, myself, Claudia Marchand, Jesus Escarcega, and Brian Mata. During this presentation, I will be going over the introduction of VVT testing methods. I will also be discussing white box system testing. We will then discuss black box system testing and its subparts, basic testing, high volume testing, special testing, environment testing, and phase testing. These portions will be covered by both Jesus Escarcega and Brian Mata. Finally, Brian Mata will end today's presentation with a conclusion of Chapter 5. Let's now discuss the introduction to Chapter 5, System VVT Methods. Let's begin by asking ourselves, what is VVT testing? VVT testing is a subset of verification and validation methods dealing with actively operating the system and verifying or validating it. Every VVT testing method has to go through a valid process. This process is broken down into 4 phases. Test cases, the tester, the system under test, also known as the SUT, and system specifications. This diagram depicts the 4 system specifications that are involved in the VVT testing process. The fundamental system testing process involves having the test case, the tester, the system under test, and lastly the system specification. The system specification includes a list of system requirements and other important elements that are the very basis for the design and building of the target system. It is important to note that there are the musts and shoulds that dictate what the system must be and must do, for which the customer is willing to pay. This is where you keep in mind the system design based on the stakeholder needs, wants, and based on the budget that has been established for the target system. Moreover, this is why it is important for a system to be evaluated and tested throughout the process at various stages to ensure the system is meeting all of its intended specifications. These same system specifications are therefore the measure by which the system must be judged. Overall, it is important to understand that the system specification includes a list of system requirements and other elements that establish the reason for the design and building of the specified target system. Systems testing. During any system testing, it must be confirmed that, number 1, the system is doing what it should be doing, in other words, conforming to the system requirements, and number 2, that the system does not do what it should not be doing. A lot of the times we find ourselves focusing on the intended purpose of the system being developed, that we forget to also identify the items or things that we do not want the system to be doing. Identifying what the system should not be doing is just as important as making sure that the system is doing what it's supposed to. That is why it is important to set specific parameters for every target system. Now let me provide you with a brief overview of what white box systems testing is. White box systems testing is also known as clear, open, structural, and glass box testing. It was given this name because it is involved with the inner workings of an application and it is focused on the internal testing of the system. White box system testing is usually undertaken with an internal or a structural view. It is usually conducted at the unit or component level, and it tends to discover structural problems. On the other hand, black box testing is a counterpart of white box systems testing. Black box systems testing, contrary to white box system testing, is mainly concerned with a functional or external view of the item being tested. It is usually conducted at the subsystem and system levels, and it typically detects functional defects. Black box systems testing is usually involved with the testing from an external and end user perspective. This is a diagram that depicts the delineation between each type of testing. White box testing, as mentioned before, is usually conducted at the unit or component level, and it usually tends to discover structural problems, while black box testing is usually conducted at the subsystem level, and it typically detects functional defects. Now I will discuss white box system testing in more detail. As mentioned previously, white box system testing is also known as structural systems testing. White box systems testing usually requires for the VVT user to have implicit knowledge of the internal workings of the system. Additionally, white box system testing is conducted through the use of special features. Let's discuss the advantages and disadvantages of white box systems testing. Some of the advantages are that it is 1. Easy to generate input data for testing the application effectively. 2. It encourages careful reasoning about implementation of the testing process. 3. It has many tools available to identify software test coverage and measure the complexity of the system's code. And 4. It's conducted through the use of special features. There are also some disadvantages to using the white box system testing. Some of these disadvantages are that the VVT engineer must be a matter expert and have the necessary skills referenced the subject matter domain. This includes specific knowledge referenced to hardware and software of the system. Moreover, he should have very specific knowledge referenced the internal structure of the system that is currently being tested. Another disadvantage to the white box system testing is that there are limitations to performing certain tests. The reason these limitations exist is due to the complexity and continuously evolving of modern hardware. Let's discuss coverage testing of hardware components or software code. Coverage testing of hardware components or software code refers to ensuring that as large of a portion possible of hardware component or software code testing of the UT, also known as the unit under test, is covered by a given set of individual tests. This is crucial in order to determine if the input test patterns will expose certain faults in the UUT. This is done by triggering the fault and making its impact visible at the output of the unit. This testing is done at the lowest unit level possible. This, in return, can save an organization money on the long run through the order of magnitude concept. Basically, this means that when a test fails to detect an error at a given level of packaging, it will cost an order of magnitude more to detect the error at the next higher level of packing. This is as a result of controllability and observability. Controllability refers to the ability to control individual inputs to individual subunits within the system, and observability refers to the ability to observe individual outputs from individual subunits within the system. It is important to note that the larger the system, the more difficult it will be to maintain observability and controllability of the system. Lastly, when it comes to white box testing, it is also important to note that the test methods for hardware and for software systems are discussed separately. This brings me to the first topic in component and coverage testing, the hardware aspect of it. Hardware testing refers to verifying that a certain test sequence has tested all of the components of a circuit and/or a system. In the scope of things, the possibility of hardware defects is extremely large, and the defects can be numerous and diverse. For this reason, there are several fault models in place to identify and manage these defects. Some examples are variability, multiplicity, and effect on function and operating speed models. Variability is a non-permanent hardware fault that may appear on an intermittent basis or in relation to transient events within the circuit. Multiplicity is when multiple hardware faults affect the behavior of the unit under test in unexpected ways. Effect on function and operating speed are faults that may affect the overall function behavior of hardware. They often manifest themselves only after a specific sequence of inputs. Some examples of hardware testing are stress testing, load testing, and installation testing. It is clear that hardware testing can be integrated in just about every item we interact with on a daily basis. Research shows that there are many ways of generating and validating test patterns. These are referred to as vectors. In component coverage testing on hardware, there are 4 different types of vectors. They are manual generation, pseudo-random generation, algorithmic generation using the algorithm, algorithmic generation using path-oriented decision-making algorithm, also known as PODEM. In manual generation, the test patterns may be generated manually by test engineers for functional verification of a UUT. In pseudo-random generation, the test patterns are generated using a random number generator and then simulated at the circuit level. In algorithmic generation using D algorithm, the D algorithm uses a single stuck-at-fault model and defines the notions of primitive D cubes of failure and propagation D cubes. Algorithmic generation using path-oriented decision-making algorithm is an improved D algorithm in the sense that its complexity grows exponentially with the number of UUT inputs and not with a much larger number of circuit nodes. In terms of component coverage testing in software, code coverage testing results can help improve test cases that will increase code coverage over vital functions. For software code coverage, there are 3 popular types. They are statement coverage, branch coverage, and condition coverage. In statement coverage, testing can verify that one or more test patterns causes the execution of each and every software code statement at least once. In branch coverage, that verifies that one or more test patterns cause the execution of each and every branch of the control flow at least once. And in condition coverage, it verifies that one or more test patterns causes the execution of each and every branch of the control flow, and that all values of constituents of compound conditions are exercised at least once. Based on our team project, the monitoring tool PMO 2.0, all 3 types of software code coverage tools will help facilitate our system to ensure that there are no internal security holes or poorly structured coding processes. Moreover, it would ensure that specific inputs are providing the expected code outputs. Now let's discuss interface testing. Interface testing are agreed upon mechanisms for interactions and communications between different parts of a system. These interactions also refer to the communication between different parts of the subsystems. There are 3 types of interface testing: hardware-hardware interface, which is communication between hardware systems; hardware-software interface, which is the interface between hardware and software; software-software interface, which is the communication between software systems; and human system interface, which are interactions between the user and a system. In interface testing, there are also categories of interaction. There are 4 categories of interaction. There are material, which identifies the needs for materials exchanged between 2 elements or systems; spatial, which identifies the need for adjacency, force transfer, orientation between 2 elements; energy, which identifies the requirements for energy transfer between 2 elements; and information, which identifies the requirements for information or signal exchange between 2 elements. Hardware interface testing should be conducted at various communication interface layers. 3 of the most common interface testing levels for hardware are physical level interfaces, which is the testing of the physical connection between different parts of the system; electrical level interfaces, which is the testing of the electrical and electronic compatibility of hardware units, that is, the compatibility of the 2 systems in terms of signal voltage, current, duration, and shape; and protocol level interfaces, which is the testing of the internal structure and format of signals between 2 or more hardware systems. Software interface testing should also be conducted at various communication interface layers. 2 of the most common interface testing levels for software are parameter interface and shared memory interface. Parameter interface is based on a protocol whereby a calling procedure or routine transfers control to another procedure together with a predefined set of parameters. Shared memory interfaces is an agreement between one software element and one or more other software elements whereby one procedure or routine may write predefined information into an agreed memory space, and other procedures may read it when they are executed. Human system interface testing. Unpredictability of users. Testing must cover the variability among individuals. Differences in human behavior are difficult to model. Systems missions. Testing must take into account what it is that the system and users will be doing and why they will be doing it, and design the testing process accordingly. In terms of system technology, modern systems tend to evolve fairly rapidly. A user's understanding of an interface technology may lag behind the technological advances. This must be considered and be attempted to assure a smooth operation of the system at hand. Lastly, operational environment. Testing must consider the physical layout of the system at hand. This concludes the white box system testing aspect of this presentation. Now, Brian Mata and Jesus Escarcega will discuss the black box system testing.